Welcome to the deep dive.
Great to be here.
So today we're looking at something maybe a bit unexpected. We're connecting some pretty abstract math calculus to, well, planting crops,
Yeah, it sounds like an odd pairing at first.
doesn't it? But we've gone through these sources, and what really jumps out is how they tackle this very practical problem. How do you plant seeds to get the absolute best yield? They call it finding the optimal planting density.
The perfect number of seeds per square meter, basically.
Exactly. And our mission today is to unpack how calculus, specifically a tool called differentiation, is actually the key to solving this.
It's a problem farmers wrestle with all the time, even intuitively. Plant too few seeds.
And you're wasting space, right? Your field could be producing more.
Definitely. You see these big gaps, potential harvest, just sitting there unrealized.
Like a big empty canvas.
But then there's the other extreme. You pack them in too tight.
Thinking more is always better.
Right, but it backfires. The plants end up fighting each other.
For what? Sunlight? Water?
Right, exactly. Sunlight, water, nutrients in the soil, all limited resources. This constant battle, this competition, it stresses the plants.
So they don't grow as well.
They don't. They might be smaller, weaker, less productive individually. So jamming more in can actually lower your total yield per square meter.
Okay, so not too sparse, not too dense. There's a kind of sweet spot.
Precisely. A sweet spot. And this is where the math comes in, according to the sources. They model this whole relationship.
Oh, so?
They show, you can think of the yield, the final harvest amount, as being a function of the planting density, how many seeds you put in that square meter.
Okay, so yield depends on density. Input is density, output is yield. Makes sense.
And typically, as you increase density from 0, the yield goes up, but then it levels off, and eventually it starts to drain because of that overcrowding we talked about.
It forms a kind of curve then. Goes up, peaks, comes down.
That's the idea. And calculus gives us the tool to find the exact top of that curve.
How does it do that? What's the tool?
It's differentiation. You remember derivatives from calculus?
Vaguely. It tells you about the slope, the rate of change, right?
Exactly that. The derivative of this yield function tells us, at any specific planting density, how quickly the yield is changing. Is it increasing?
Decreasing? Or is it momentarily flat?
Yes. And that's the aha moment from these sources. At the very peak of the yield curve, the absolute maximum yield point.
The slope is 0. The rate of change is 0 right at that instant.
Precisely. The curve is neither going up nor down at that single point. It's flat for just a moment. Straight into solving a really important problem in agriculture, one with real economic consequences for farmers and food production.
It just shows this math isn't purely theoretical. It's a powerful tool for optimization in the real world.
It really is.
Yeah.
And it makes you wonder, doesn't
I
it?
wonder what.
Well, if calculus can pinpoint the single best planting density like this, where else could